Alright, are we live? Okay, are we live? Can I get a sound out from the chat? Any is the audio available for everyone to hear? Okay. Alright, if you guys can hear, can you give some comments in the chat room? Alright, that would be really helpful. Right. Is the audio up to par, and are the settings ready for us to go? Can give an indication inside the chat room. Alright, awesome. Okay, great. Welcome everyone to the live stream for Discrete Math, our final live stream. Of course, for those of you who are having the exams tomorrow, we're gonna do a Q&A today. But for the rest of you who are joining in because you're curious as to what this is about, basically during the first half, or during the past few weeks, I've been teaching a Discrete Math course at the university at which I graduated. So I'm just running a question and answer for my students. But feel free to raise any questions you wish as well. Alright, so here's the first question. We have this little sneaky claim that we can do this really strange property where you could basically bring the power into the expression, okay? And here's the proof of which we're doing that. Here's the quote-unquote proof of the result. We're gonna prove starting from the base case, and we're gonna prove it using induction. So the base case is given by n equals to 0, and for the induction step, we're gonna use strong induction. Okay, so the base case n equals to 0 means that, well, on the left side we get x naught squared, on the right side we get x naught squared as well. If we submit n equals to 0 into this expression, all is well. So we have that first and foremost. For the induction step, we're going to suppose the result holds for n equals to 1 all the way, well, n equals to 0, 1 all the way up to k. So we're going to try to prove the situation for k plus 1 up to k plus 1. We can treat this whole expression as two terms, and we know that since x naught plus x1, by induction this should be true. We can split this up accordingly. Some of you might know where we are going with this, but for those of you who know the answer, you can keep it there first. And next up, we can use the induction hypothesis for the term n equals to k, which lands us with this result. And therefore, we have allegedly proven the result for the induction step, which tells us that this is true for all natural numbers. And it turns out that there is a little sneaky problem with this argument. For those of you who sort of realize what's going on here, this is the step where it fails, right? So we suppose that the result holds for n equals to 0 all the way to so on and so forth. So in particular, we should try to prove the case when n equals to 1. Right? In other words, we should try to prove that x naught plus x1 squared equals to x naught squared plus x1 squared. However, the base case doesn't actually prove anything over here. It doesn't actually get us anywhere. Okay, and because the base case does not get us anywhere, it turns out that this is actually false. Very simple counterexample. You take 1 plus 2, you square that, you compare that with 1 squared and 2 squared. On the left side, you're going to get 3 squared. On the right side, you're going to get 5. So you're getting 9 equals to 5, which is obviously a contradiction. So it's quite evident that turns out that this is the sneaky step which actually fails. Right here. Okay, so this is actually the step that fails. Now, for perhaps some of my other viewers who are interested, who are math nerds and who are interested, it turns out that this result actually still works in what we call the field of two elements. Okay, so I'm not going to detail this for my discrete math students here, but it turns out that this is true inside this particular number system. Right? For those in discrete math, you don't have to worry about this at all. Right, so this is sort of an abuse of mathematical induction. It turns out that we actually can't prove this result. It's not really a true result, and the argument breaks down. But if we're not careful, it's hard to actually identify where the argument breaks down. Alright, now we're going to look at two more questions involving paths and cycles, and once we are done with that, we're going to open the floor to any kind of Q&A. But these questions are interesting because they highlight, the first question highlights the utility of thinking in terms of math induction as a problem-solving process, and the second one helps you think in terms of chopping things up as a technique. Okay, so let me explain what do I mean by that. So here's the claim. So here's the claim. We'll let P be a path in G, then the number of edges in the path is the number of vertices in the path minus 1. Now, interestingly enough, a path is what we call acyclic and connected, and therefore it's a tree, and therefore this actually gives you the tree form. This is actually a consequence in a sense of the tree formula. But let's assume we know nothing about the tree formula. If you want to watch a tree formula video, I have it somewhere on my channel. You can go check that out. But assuming we know nothing about the tree formula, we can actually prove this from scratch. Right, so here's the idea. We're going to use induction to help us prove this result. So let's just assume that the number of vertices is at least 1. Let's just assume that the path has at least one vertex. Now, what does that tell us? That is going to tell us, okay, we can try to prove by induction on the number of vertices. So, okay, so here's the idea. Let the number of vertices equals to n for some positive integer, and we're going to prove this by induction. So base case is when n equals to 1. Then the path, right, will be, so we'll let, I guess we can use x1, denote the vertex in P. And we know that P is a path, and therefore it cannot contain any cycles, right? So in other words, we know that we claim that EP that the path has no edges, right? So the claim is that this is empty. And how do we establish this claim? We're going to establish this claim in this manner. Suppose otherwise that there exists some, let's say, edge E inside the path. Well, since it's an edge, it has to connect points inside the path. But there's only one point in this path, right? Because if n equals to 1, then this tells us that we only have one vertex. Then E must equal to the edge x connected to itself. But it tells us that P has a loop, which is a contradiction. So therefore, the path actually has no edges, which tells us that it has 0 edges, but that means this equals to 1 minus 1, which is the number of vertices minus 1. So that's sort of the base case that establishes the base case. Do we need to practice the induction corner questions? Not sure what that means. You might be referring to the L Tromino trick, which I have somewhere else in my channel. I'm not too sure what that means. Okay, so we're going to go ahead with the induction step. So induction step. So we're gonna suppose the path has n plus 1 vertices. Right, so the idea is that suppose it has n plus, or rather k plus 1 vertices. And the idea is that the result holds true for any path with k vertices. Now, what I like to do here is, okay, so we let the path be denoted by x1, x2, all the way to xk plus 1. And this is all really symbolic, so I like to visualize this as follows. And try to ask myself, what can I do in order to take advantage of the induction step? In other words, how can I convert a path of length k plus 1 into a path of length k? Well, the idea is to basically chop this up, right? Chop it up and consider what remains as a path of length k. So what we're going to do here is define the path q, right, by this path. Now, I believe you can denote it this way. If you want to be a little bit safer, you could try to spell everything out in terms of vertex sets and edges, but I think this gets the point across. Why is this useful for us? Well, this tells us that Q is a path and its number of vertices is k. It has k vertices. Now, if it has k vertices, what does that tell us? If it has k vertices, this tells us that the number of edges in Q by induction, by the inductive hypothesis, is the number of vertices minus 1. Okay, so that tells us it has k minus 1 edges, which should make sense, right? Because the number of edges here is basically k minus 1. Okay, so that's really useful. So how do we sort of recover this little bit over here? Well, if we look very carefully, the vertices of P are the vertices of Q with the inclusion of the extra vertex x sub k plus 1. And the edges in P are the edges in Q, including that last edge that we essentially chopped off. And so when you have that, what does that tell us? We know that these two sets do not overlap. So that tells us that the number of vertices in P is the number of vertices in Q plus 1. And the number of edges in P is the number of edges in Q plus 1. But we do know that the number of vertices in Q is k, because Q has k vertices. And the number of edges in Q is k minus 1. We've established that just now. So the number of edges is k. The number of edges in P is k, but that simply means that we get this result. And by algebra, we are good to go. Okay. So the idea here is to sort of use this chopping off technique to help you recover the result that you're trying to solve. You sort of take the big version, you chop up some not so useful parts about it, you slap on the induction sort of conditions that you're allowed to use, and then from there you're able to sort of proceed. You're able to proceed on with what you're trying to prove. Right, so that's the idea. You sort of want to take the bigger graph or the bigger path or whatever you're working with, chop it up into smaller bits, slap some induction results, and recover the main result. Really useful idea here. On that note, we can talk about cycles. So we're gonna let C be a cycle, and we need to prove the claim here is that the number of edges in C is the number of vertices in C. Once again, you could take a particular sort of approach to this, what I like to do is to you could use induction on this. It's actually a really good exercise for you to try to use induction on this. And of course, we know that every cycle has at least 3 vertices. Now, I'm not actually going to use that result here. I don't actually need that, but we can use it anyway. So we're going to let C be the cycle x1, x2, x, let's just say n minus 1 and xn, and we need to return back to the original, right? Again, this is the notation, and the picture is a little bit more useful for our purposes. Like this. Now, what I have in mind here is that because of the definition of a cycle, at least within discrete math that we're doing, there are actually no overlaps here. You actually cannot overlap anything. So my idea is to sort of chop off this edge here, and what remains is a path. Right? So define D to be the path x1, x2, xn minus 1, xn. So sort of you chop off that very last edge. Right? Well, since it's a path, and we know that v of D, well, we know the number of edges in D is the number of vertices in D minus 1. However, we also know that we do know that based on this construction, the vertices in D actually are the exact same vertices as the vertices in C, and the edges in D are the edges in C, or rather, we'll phrase it this way. The vertices in C are the same as the vertices in D, and the edges in C are the edges in D, including that last edge. Right. So what that tells us is that the number of edges in C is the number of edges in D plus 1. But we've already seen from the previous result that this is the number of vertices in D minus 1 plus 1. And this simplifies to the number of vertices in a number of vertices in D. Yep, correct. But we also see that the number of vertices in D equals the number of vertices in C. But when we place all of that together, we actually get the result that we were trying to prove. So those are the questions that I wanted to sort of discuss. Feel free to raise questions about that as well. And we're gonna proceed with the questions. Feel free to type your questions into the chat room, and we will we'll discuss those in just a moment. I have no idea whether there are ads, but if there are, it is what it is. Okay. All right. So feel free to now raise your questions in the chat room. I have no idea what is this question. I genuinely have no idea what this question refers to. Could you send it over to me? Take a photo and send it over, or something, or whoever has the question can send that over. I think it's a graph question, probably. That's my guess. Or is it a cardinality question? I'm not too sure. Okay, are we talking about the question pertaining complete graphs? Are we talking about that question out of curiosity? Okay, so here is the question. We're gonna let k and n be natural numbers. We're gonna assume that k is not more than n, and we are gonna consider kn. What this refers to is a complete graph. This is a complete graph on n vertices. Right? And we're gonna ask for the number of subgraphs and the number of paths, right? So we are interested in two questions. One, number of subgraphs with k vertices. That's the first question. And the second question, right? The second question is the number of paths with length k. Okay, so let's think about this in a bit of with a little bit of precision here. So number of subgraphs with k vertices. Now, a subgraph is essentially right, it's a smaller graph, right? So kn, just to recall everyone, let me just draw n equals to 5 in the case of n equals to 5. Looks a bit like this. Like that. And what we want to do is find the number of subgraphs with size k. So let's just say I'm using a size 4 graph? Well, we have for a graph with 4 vertices, there are actually 5 choose 4 ways to choose the vertices. 5 choose 4 number of ways to choose the vertices. So the number of possible choices of vertices is n choose k. We can choose any k vertices if we wish. And then what do we have afterwards? Well, the total number of edges inside such a graph is going to be the number of vertices choose 2. Right? So in this case, we get 4 choose 2 because, well, this itself has, these are all the different possible edges you could create. So the number of edges in the subgraph is k choose 2. Now, to obtain a graph, we need to have a collection of edges. So how many edges could we possibly create? Well, we need to ask how many possible choices of edges, or in this case, how many subsets of edges can we make? Well, that's just basically 2 to the k choose 2, because that's the total number of edges we could make. This tells us that the total number of graphs, total number of subgraphs, the total number of subgraphs is the total number of choices of our vertices multiplied by the total number of edges. Multiplied by the total different possible edges that we could create from it. Right. So I believe that is our answer. That's the thought process that I took when doing this question, and I am now going to check the solutions just to make sure that we're on the right page for this. I think we should be right, but let me just do a quick verification here. Yep, looks about right. Okay, and the next question is to ask for the number of paths with length k. It might be actually helpful to once again refer to this diagram for our own reference. Again, this helps to give some kind of intuition about the problem. So the idea of a path is that if you have a length 4 path, let's just say we're looking at the length 4 path, then what we have here is we could choose any sequence of vertices. So we could choose 1, 2, 3, 4. This could be our path. We could also choose 4, 3, 2, 1. But if you look really, really carefully, these two represent one and the same path. Now what it tells us is that the total number of paths is going to be the total number of permutations of these vertices. How many ways can we, how many permutations can we form? Well, that will be n choose k times k factorial. Right, you choose the vertices you want and you find the number of ways to permute it. But because there's a repetition here, in the sense that these two permutations, as permutations they're different, but as paths they're identical, we need to multiply this by a half. And furthermore, this only works if your length, if your path really has length k and it's smaller than n. Right? So the idea is that what happens if k equals n? In other words, if you have a path of length 5, you're actually going to end up with a cycle one way or another. So the idea is that paths, we do not allow them to have cycles. So therefore, if your path has length 5, right, you're going to get a cycle and therefore you won't get any paths. So there is that. Yep, so that's that. That's the question. So hopefully that sort of clarifies the thought process behind this question. I wanted to approach it without sort of having prior knowledge to it, so that you know what's going on in the back of my mind before I actually go ahead to solve the problem. Answer for tutorial 10.5 BCD. I believe I've done that in a previous live stream. Yeah, I think I have it on one of my live streams, but we can look at that nonetheless. So this question is pertaining the relations. Okay, so a very classic question here. Number of relations. So fix m as a positive integer. Let a be a set of size m. How many relations do we have on a? Now I'm gonna make things a bit easier. I'm just gonna say that a is 1, 2, all the way to m. Alright, without loss of generality, I think we can do this. Right? So, how many relations do we have on n? So a relation on n, a relation on a, right, is basically a subset of a. So the number of subsets of a, right? Sorry, is relations on a subsets of a cross a. Pardon me for that. Well, we have a number for that. That's just basically 2 to the a cross a. It's 2 to the that. That's the first part of the question. Naturally, we're gonna ask the question: how many reflexive, symmetric, and anti-symmetric relations do we have here? So, number of reflexive. I noticed there are many people who asked me this question in the past few days because people are a little bit confused with what's going on. Okay, so what's a reflexive relation? Just to recall, a relation is reflexive, right? With the property are relations such that any, or rather relations that contain any sort of loop, right? Reflexive relations are the relations that contain the loops. And these are actually represented by these guys here. These are represented by these particular points. This point here represents the connection from 1 to 1. This point represents the connection from 2 to 2, so on and so forth. I'm going to call this the diagonal. Right? So the idea is that my relation must contain this diagonal. I don't care what relation it is, in order for it to be reflexive, it must contain this diagonal. So in other words, it is all of the different relations of the form, let's call this D, D union S, where S is any subset of everything else. So I want to reiterate here. The reason why we're writing it this way is because every relation that is reflexive must contain the diagonal. It may contain the point 1m, the connection 1 to m. It may not. It may contain the connection m to 2. It may not. We don't really care. In other words, we are looking at essentially, no matter what relation we are looking at, in order for it to be reflexive, it must always contain this diagonal. So where do we have free choice? We have free choice over all of the other terms over here. Does that make sense? In other words, the number of relations is precisely the number of subsets of A cross A excluding D. Every relation that's reflexive, for every relation that's reflexive, you can find one of these subsets. And for every one of these subsets, you can form a reflexive relation. So what that means is that the total number of relations that are reflexive are the number of subsets of the off diagonals. Because all of these relations will definitely always include the diagonal. Does that make sense? It will always include the diagonal no matter what. From that point of view, you get 2 to the A cross A excluding D. Right, so 2 to the m squared minus m. Because there are m items in D. That's the reason why we care about the subsets of the diagonal, because every relation is comprised of the diagonal plus some union with some subset of the off diagonal. So that's sort of the reason behind it. Right, so from that point of view, you might be able to see how to approach the rest of the question pertaining symmetric relations and anti-symmetric relations. I will let you guys check that out in the live stream inside on YouTube somewhere there, right? So the live stream is somewhere there. Yeah, but hopefully this clarifies the number of reflexive relations because I think I can see why it may have been a little bit confusing for that. Let me know if you want me to go through the rest in more detail as well. I'm more than willing to do that, right? But yeah, that's it for now. I believe. Yeah. Why don't we consider the different combinations? So here's the idea. If we have a relation that looks like this, let's just say it just stops at m-1, m-1. Then we run into problems because then what about mm? In order for a relation to be reflexive, this relation must include every single pair. Right? That's what it means for a relation to be reflexive, right? So we say that R is reflexive precisely when for any x in A, xx belongs to R. But if we are missing at least one of these items, then we are not going to be able to get a reflexive relation. So that's that lah. Yeah, that's that. Alright, cheers. All good. Right. I think I covered most of the other tutorial questions on the live streams already. So the only ones that have not been covered are the ones that I've discussed today, which is the induction question, as well as the paths question and the cycles question. Everything else I've pretty much covered it elsewhere. I might have skipped over some details, but essentially there's that. When can we not use the result for 9.7? What on earth is the result for 9.7? You know, just a favor, if you guys can help me. I don't remember these theorem numbers. I really don't. Yeah. Okay. Anyway, 9.7. When can we always use it for all proofs about countable sets? Yep. Sure. Anything that you have solved at the tutorial level, you can use it freely during your exams. That's basically it. As long as you have done it on your tutorials, you will be able to use it in your exams. When can we not use the result? No, I know you can use it anytime you want. Yeah. I think the real question is how useful the result is. It can be useful. You don't have to quote the theorem number, by the way. There is one exception though. If you're ever using the eating up lemma, please do not use the phrase eating up lemma in the exams because I'm not the lecturer, right? So instead of using eating up lemma, which appears quite a bit in the graph theory segment, don't use eating up lemma. Use by the proof of theorem 13.1.7. you can continue on the argument, which essentially basically says that you're using the eating lemma, right? But otherwise, I don't think you need to do any kind of justification for the other kinds of proofs. I don't think there's a need for it. Yeah. How's everyone doing? How's revisions for discrete math coming along? For those who are interested, I am dropping a new video on Thursday. I drop a new video every Thursday on completing the square. At least this Thursday is on completing the square. What are the most important techniques you should know for counting? Logic. I know it sounds a bit strange, but you know. And again, the question here, I believe, sort of the underlying idea is there sort of like a fixed structure to it? You know, is there sort of a very cut and dry, copy and paste kind of strategy to counting? My general answer to that is no. My general answer to that is that you need to figure out what's the steps, or rather, you need to break down your problem into a bunch of different components. Each of these components have a particular calculation for them. Right, so, for example, this particular case on counting reflexive relations, there isn't really a formula for it apart from the number of subsets. But the idea is you want to break down the problem of relations into the diagonal and the off diagonals. So that's the important bit. In that regard, that's a little more important than a particular formula. I know in high school, you know, most of our success, we derive it from we always try to derive it by drill and practice, right? You could do that, but you're not drilling and practice techniques. You're like, you know, writing you're drilling and practice your thought process. Is counter to double counting always divided by 2? Yes, because that's the idea of double counting, right? Every sort of thing you considered to be different turns out actually to represent the same object. In that sense, with double counting, you need to divide by 2. But that being said, it's not entirely obvious sometimes when to divide by 2, right? You have to be able to identify that you are counting repetitions. And if you do notice that, you divide by 2, right? Sometimes the repetitions appears in 3s, and 4s, and 5s, and that's where you need to think a little bit more about. Yeah. Any other questions from the chat room? I don't think there are people who are not from discrete math here. I believe everyone here is from discrete math. But if you're not from discrete math, just shout out. I guess I can do a bit of marketing for some of my future videos. Again, for example, how do you complete the square? Right? Turns out there's a really easy way to do it. You just need 2 things. You need the recipe and the dish. So the recipe is given by the negative of this number divided by 2, and the dish is derived by plugging in this number into the equation. Right, so this gives us 1, I believe. This gives us 1. Right, so that's how you complete the square relatively quickly. It's really, really fast. That's one of my videos I have upcoming. Another video I have upcoming is matrix multiplication. So for example, how do we multiply this, make this calculation you could sort of go through a rote memorization process, but turns out that the strategy to do this calculation lies in recipe dishes once again, right? I think of this as the recipe ingredients. These are recipes, these are your ingredients, and then you sort of use the recipe and the ingredients to create your dish. Yeah, and in fact, this time the recipe dish analogy is even more pertinent compared to like before. So okay, welcome. Decide if the value of a, yeah, this is nothing to do with discrete math, but well, more than welcome, mate. Okay, so decide the value of a if this thing. Okay, so let me just write down the equation here. This is x squared plus 2ax equals to 3a squared minus 1. I believe this is the question which you're interested in. And I believe what we mean by this is what is the value of a if we're given that this equation. I think we're asking whether this equation has a unique solution. I think that's the question. If this has a unique solution, right? So the question is that this equation should have one unique solution. This equation itself doesn't really tell me anything. This equation is just an equation. But if it has exactly one solution, we can work this out. So if it does have exactly one solution, out of curiosity, are you familiar with the notion of discriminants in high school and whatnot? Does that sound familiar? Oh, by the way, ads are coming up, so you gotta check that out. So I don't know what I'm not sure what you have learned or not yet learned, but I'm going to approach this using the idea of discriminants. And an ad is gonna be released soon, so I'm just gonna mention that. So you won't get too caught off guard. Let's see if we can solve this before the ad comes up. So I'm gonna bring this whole term over to the left side and calculate the discriminant, which is b squared minus 4a c. And the idea is that if this equation has a unique solution, the discriminant should equal 0. But we will solve that after the advertisement. Okay, so I believe the advertisement, hopefully that's sort of settled. We're going to solve this particular equation, so we're going to get 4a squared minus 4 plus 12a squared. This is going to simplify to 16a squared minus 4, which simplifies to 16a squared equals to 4. This simplifies to a squared equals to a quarter. And from that, we can take square roots to get a being plus or minus the square root of a quarter. And a is plus or minus half. So the strategy I would have approached to solving this question is to recall that in order for a quadratic equation to have a unique solution, we need to solve a quadratic equation, right? Or rather, we need to first write it in the usual standard format of a quadratic equation. And for this equation to have one unique solution, the discriminant equals to 0. On the other hand, the discriminant is given by b squared minus 4ac. Let me write that down in more detail. The discriminant is b squared minus 4ac. And if that's the discriminant, then we can sort of simplify this using a bit of algebra and obtain a equals to plus or minus a half. Alright, so hope that answers the question. Yeah, check out all the other stuff. I have a video on completing the square coming up on Thursday. At least in Singapore, that's at 8:45 a.m. But I'm not sure what's the equivalent in other time zones. So that's That's the question. Yeah. Okay, back to discrete math. For the practice paper, there was one question that maps this. Can I take the formula then? Well, sort of. I believe one of our classmates actually looked at this question the other day. So I believe your relation. More power to you, mate. Have fun. Have a good one. Okay. So where are we? Yeah. So let's go back to the past year paper. Where are we? Okay. Let's look at this particular question. I think the question is from R to D formula function. Yeah, it's all good. We need to prove the injectivity of the map. Okay. So we have a function that goes from this, right? F of y equals to I believe it's okay, I think we have to be careful here. Are we referring to this map? Or are we referring to this map? Because I believe that these two maps appeared before. Are you referring to the first one or the second one in our question? Can you give it a simple example of proving something via induction versus via strong induction? I always say that strong induction, you use that when normal induction doesn't work. I'll give an example later. Yeah, but it's going to sound a little bit abstract. Okay, so I will give an example in a moment. But let's look at this question again. For the person for the R to D question, are we referring to the first function or the second function? Is it A or B? Out of curiosity. Okay, both. Now, if we're doing part A, we actually do get a surjection, right? Because for any Z in D, or rather, let's just call this W in D, W equals to T negative T for some T in R. Choose Y equals to T. Rather choose X equals to T, then f of X equals to f of T equals to T comma negative T equals to W as required. So that's surjectivity. And for injectivity, fix y1, y2 in the real numbers, and suppose f of y1 equals to f of y2. Then by definition, f of y1 is that, y2 is that, which means that in order for the coordinates to match up, they must be the same. So we do get injectivity. Now, for part B, it's a little bit annoying because the square function actually messes everything up. Right? So the squaring actually messes everything up. If you just did it on its own, it's actually pretty doable. But the problem is once you have this squared term, things get a bit annoying because the squared term cannot be negative. So actually we don't get surjectivity. It's not surjective. The reason why it's not surjective is because choose W equals to negative 1, 1. Right? But for any Z in real numbers, Z minus 1 squared is non-negative, and therefore it can never equals to negative 1. So we actually don't get surjectivity. And likewise for injectivity, the squared expression messes everything up once again, because when you square it, right, you can have two different inputs that give you the same output, right? Two different recipes gives you the same dish. So we're gonna choose Z equals to 0 and Z equals to 2. in both cases, z minus 1 squared equals to 1, which means that f of 0 will be equals to 1, negative 1, which is f of 2. In other words, you get two different inputs that get you the same output. Therefore, not injective. It's not injective. It's not actually helpful here. Right, so that's how we work with it. Now, interestingly enough, because of the first bit over there, I believe you have a question on cardinality. If I recall correctly, the paper has a question on cardinality. You can actually use part A to establish that some connection in terms of cardinalities. You can actually do that right away. So I think that's pretty cool. All right, any burning questions from the audience? I don't know if this room is actually gonna close in like 3 minutes or whatnot, so feel free to raise that. For proving that A has the same cardinality as B, we need to prove that the function A to B we define as a function. In general, if it's pretty obvious, we don't really care. But then if it's not obvious, then you need to establish it, right? So obvious things looks a bit like this. Like this is clearly a function. Like there's no debate that this is a function. So there is that. If you can, as long as the meaning of your symbols are unambiguous, that's the main question on the function. That's the main aspect about a function. Yeah. All right, any burning questions from the audience? Any burning questions? Okay, going once, going twice, and going thrice. All right. Okay. In that case, thank you everyone for joining the live stream. Hopefully you found this to be rather informative. The entire stream will be online, so you can check that out. And that's it for today. All the best for your paper. And of course, I might do another Q&A in the future, but probably not discrete math, right? Just other kinds of things. I guess anyone else who is doing discrete math next semester, they can refer to the suite of videos in this channel. So thank you all for watching. I'll catch you guys when I catch you guys. All the best. How about induction? Oh, no, I forgot the induction question. Right, come. Let me end off with induction. Now, so here's a simple question. Claim every number is a product. It can be written as a product of primes. So maybe I'll give a few examples. So for example, the number 12 can be written as 2 times 2 times 3. The number 18, for example, can be written as, well, let's just use a different number. 30 can be written as 2 times 3 times 5. Can you prove that every number can be written as a product of primes? We're going to prove this by induction. In fact, you're going to notice very quickly that strong induction is going to be a bit painful. Okay, so here we're going to say every number that's bigger than or equals to 2. We're going to use the base case as 2. So for n equals to 2, well, 2 is itself, right? It is is basically itself. So, you know, for any prime number, you can write it as itself. That's fine. What about for any larger number n? So n equals to k, k plus 1. If you only assume that n equals to k, you run into problems because there's no real way to connect the two ideas together. Right? Pluses and times really don't really work together. But what we can do is that for induction hypothesis, we can suppose two situations, right? Suppose either n is either k plus 1 is prime or not, right? Now if k plus 1 is prime, then you can write it as a product of primes, namely itself. But if it is not, then you can write k as pq for some integers p and q smaller than k. If you only assume regular induction, you know nothing about p and q. But under strong induction, p is a product of primes. Q is also a product of primes. You don't get this if you only assume normal induction, regular induction. Now, why is this useful? That's because if you have k being equal to p times q, you're getting a product of primes times another product of primes. What does this give us in total? This gives us yet another product of primes. So, therefore, or rather k plus 1, I should write this as k plus 1, not k. Apologies. Right? So therefore, using induction, because everything prior to that sort of leads up to the k plus 1 case, you have proven that every single number can be written as a product of primes. So this is an instance of induction where induction actually fails in the sense of regular induction doesn't give you enough weapons, but stronger induction does. Okay, so that's just the general rule of thumb. You use strong induction when regular induction does not work. That's basically it. Alright. Are there any more burning questions from the audience? Alright, so I sort of nearly cut out the induction bit, but thanks for reminding me about that. Alright, so for the final time, going once, going twice, going 3 times. Okay, if there are no other questions, thank you all for watching, and I'll catch you guys when I